Our next application of differentiation is going to be two named theorems. Really, they're closely related. We've got Rolle's theorem and we've got mean value theorem. Rolle's theorem is actually just going to be a special case of mean value theorem, but this one's a little bit easier to kind of pick up intuitively and see why it actually makes sense. So Rolle's theorem is going to have a bunch of hypotheses that we have to show are satisfied, and then we're going to get some type of conclusion that involves the derivative of a function. So we're going to let f be a function that satisfies the following hypotheses. First, the function has to be continuous on a closed interval. Then it has to be differentiable on an open interval, so you don't need a tangent line to exist at the endpoints. The third thing is what's special to Rolle's and makes it different than mean value theorem is you need the y values at the endpoints of the interval to be exactly the same. If you can guarantee all of these things happen, Rolle's theorem then tells you there's a number c inside our interval so that the derivative evaluated at c is equal to 0. So picturally, this will be a little bit easier to explain. If I look here, I've got these two y values. At a and b, the y values are exactly the same. What Rolle's theorem tells me is there is some point, because of this continuity, I come back up, I have to go back down. I'm guaranteed that I'm going to have a flat tangent line somewhere inside of here. And so this is really useful for us because this value of c is going to correspond to a local max. So this is telling me I have a local max at this value. So let's take a look at another example. I've got these two endpoint values. They're exactly the same y value. If I leave and come back down, if I go up, doesn't matter. Because I have to return to this value, I'm going to have a point where I still have a flat tangent line. So there's one value here and another value here where the slope of my tangent line is equal to 0. So this is my C1, and I have another value, C2, where I have a flat tangent line. And that's where I have two different extrema. Another possibility is maybe you just have a straight line, so the endpoint values are exactly the same. Regardless of the point you pick, the tangent line has no slope because it's a flat horizontal line. So if your function is just some constant, the derivative is equal to 0 everywhere. So c is really any number between a and b. Okay? So this is really nice for us. Rolle's theorem is guaranteeing that we have a critical value between these 2 points, and we want that. We want critical numbers. We know those correspond to possibilities for local maxes and mins. Okay? But to be able to apply Rolle's theorem, I need to show these hypotheses are satisfied. So I have to verify all of these things happen. So let's try an example. Let's verify this function satisfies the hypotheses of Rolle's theorem on the interval from 0 to 3. Then we want to find all numbers c that satisfy the conclusion of Rolle's theorem. So first things first, I need to go back up here. My two first hypotheses deal with continuity and differentiability. Because this is a polynomial, it's continuous and differentiable everywhere. So I need to state these to be able to apply Rolle's theorem. Since f is a polynomial, it's continuous and differentiable everywhere. So my first two hypotheses are satisfied. Further, I need to see what happens at the endpoints. If I plug 0 into this polynomial, that would be 0 cubed minus 0 squared minus 6 times 0 plus 2, which gives us 2. And if we plug in the other endpoint, that would be 3 cubed minus 3 squared minus 6 times 3 plus 2. That would be 27 minus 9 minus 18 plus 2. Well, 27 minus 9 is 18. minus 18 is 0, add your 2, the y value here is 2. So indeed, the y values at the endpoints are equivalent. So my first 3 hypotheses are satisfied. So by Rolle's theorem, there exists a number c inside the interval from 0 to 3 such that the derivative evaluated at c is equal to 0. So I guaranteed I have a critical number, okay? So now the second part of my directions ask me to find all the numbers that satisfy the conclusions. So I'm going to go through and I want to find where does the derivative actually equal to 0. So to do that, I need to actually take the derivative. So here is our function x cubed minus x squared minus 6x plus 2. Our derivative is 3x squared minus 2x minus 6. We want that to equal 0, so we can go ahead and use the quadratic formula. So that would be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we go through and simplify this, that would be 2 plus or minus, that would be 4 plus 72, so it would be root 76 divided by 6. Okay. So ultimately the values of c would be exactly these, 2 plus the square root of 76 over 6, and 2 minus the square root of 76 over 6. But if you plug these into a calculator, you're going to see the first one is about 1.786. The other is negative 1.1196. And this is not the one that's guaranteed to exist by Rolle's theorem, because this is not in the interval from 0 to 3. Okay. So let's try another example. We want to determine whether Rolle's theorem can be applied to the function f of x equals the absolute value of f minus. Okay. So let's try another example. This time we're not told to show it satisfies. We're asked to determine whether Rolle's theorem can be applied to the function f of x equals the absolute value of x minus 5 on the closed interval from negative 2 to 2. If it can be applied, then we want to find all the numbers that satisfy the conclusion of Rolle's theorem. So we have 3 things that have to be satisfied. First, this is an absolute value function. F is definitely continuous on the interval from negative 2 to 2. If we look at the endpoint, if we plug in negative 2, that would be the absolute value of negative 2 minus 5, which is 2 minus 5, or negative 3. If you plug in positive 2, it's the absolute value of positive 2 minus 5, which is still 2 minus 5, or negative 3. So those two do satisfy that the endpoints of the interval are equal to each other. But the problem lies in f is not differentiable. On the interval negative 2 to 2. So if you go to graph this thing, it is the absolute value function just shifted down 5. So your graph would look something like this. And you've got that sharp corner right here at 0. So that means it's not differentiable at 0. and 0 falls in that interval from -2 to 2. So we fail this hypothesis. F is not differentiable in that interval. Because I fail one hypothesis, Rolle's theorem cannot be applied. Okay. So it only has to fail one thing to not be able to use Rolle's. All right, so the next thing we're going to go over is the mean value theorem, which is really a generalization of Rolle's. So this one's not as easy to kind of understand why it happens, but it still kind of deals with what our derivative represents. So you have similar hypotheses that need to be satisfied. So we need f to be a function that satisfies two things. First, it needs to be continuous in our closed interval, and it needs to be differentiable in the open interval. So I don't have that third condition anymore. The endpoints don't have to be the same. What mean value theorem tells me is then there's a number c in the interval such that my derivative is equal to the difference in y values over the difference in x values. Or equivalently, that's the difference in the y values is the derivative times the difference in x values. So really what Rolle's theorem tells you is these two are the same, which means this fraction would equal 0. So you get the derivative is equal to 0 for Rolle's theorem. So it's really just a special case of mean value. If you think of the word mean, it kind of talks about average value. So remember this right-hand side is just going to be the slope of a secant line. It's what we use to come up with our derivative. So geometrically, this has an interpretation based on that graph of the function. So geometrically, this means the average rate of change, which is that slope of the secant line, is equal to the instantaneous rate of change at some point inside your interval. So instantaneous is the derivative, the right-hand side is that secant line. So to kind of show you that yes, that does happen, let's look at a function. So this would be our value of f of a, this would be our value of f of b. If I go ahead and connect these two endpoints from a to b, this would be our secant line. So it's on average how much that function is changing from point A to point B. What mean value theorem is telling you is that there is some c value, which is an x value, between A and B, that if I take the tangent line at this point, it's going to have the exact same slope as that secant line. So these two are going to run parallel to each other. Okay? So this would be our tangent line at the point C, f of c. Okay? So my tangent line slope has the same slope as my secant line. Okay? The slope of the secant line from A to B is the difference in the y values over the difference in x values. And since f prime of c is the slope of the tangent line at the point C, f of c, mean value theorem is just stating there is at least one point P so that the slope of the secant line is the same as the slope of the tangent line. So this would be our point P, that we're guaranteed the slope of this line is the same as the secant line. Okay? And there can be multiple points where that happens. So if we look at this picture, if I go ahead and connect these two, that would be my secant line. I really have two different points, one here and one here, where if I go ahead and draw the tangent line at those points, they run parallel to my secant line. So this would be one value of C, another value of C, guaranteed to exist by mean value theorem. Okay. So the same kind of idea applies. You have hypotheses that have to be shown, then you get some conclusion. So your actual solving of problems is going to be similar when you're asked to apply mean value theorem versus Rolle's theorem. So we're going to start with an example. We're going to verify the function 1 over x satisfies the hypotheses and mean value theorem on the interval from 1 to 3. And then we want to find all numbers of C that satisfy the conclusion. So first and foremost, f of x equals 1 over x is a rational function. So it is indeed continuous on its domain, and the domain includes 1 to 3. So I've got the continuity that I need for the first part. Second piece, it's differentiable everywhere except 0, because that point is a problem. And that interval includes the one we're talking about from 1 to 3. So by mean value theorem, there exists a number C inside the interval from 1 to 3 such that our derivative is equal to the difference in the y values at the endpoints over the difference in the x values. So I can clean this up a little bit. My function evaluated at 3 is 1/3. Plug in 1 is 1. And then the bottom, 3 minus 1 is 2. If you do 1/3 minus 1, that's negative 2/3. We divide that by 2. Taking negative 2/3 and dividing by 2 is the same thing as negative 2/3 times a half. So the halves cancel. And basically, I'm guaranteed that my derivative is going to equal negative 1/3 at some point in 1 to 3. So this is the conclusion of my mean value theorem. I'm guaranteed there is a number C inside the interval from 1 to 3, so my derivative has slope negative 1/3. The second part of our statement says to find all the numbers that happens for. So now I want to see, where does the derivative equal negative 1/3? Okay. So since our function f of x is 1 over x, which is really x to the negative 1, we have the derivative f prime is applying that power rule, negative 1 x to the negative 2, or negative 1 over x squared. Okay. So we need the derivative, negative 1 over x squared, to equal negative 1 over 3. So going ahead, cross multiplying, this would give you negative 3 is negative x squared. So crossing those, multiply by negative 1 to give us 3 is equal to x squared. And then taking a square root, you get 2 answers, plus or minus root 3. So the values of C that satisfy the hypotheses would be square root of 3 and negative square root of 3. So these are the two values where my derivative is equal to negative 1/3. But this one we don't care about because this is not in the interval from 1 to 3. So ultimately, the value of C that satisfies the conclusion is C equals the positive square root of 3. Okay. Now, mean value theorem has some kind of other useful techniques and kind of interesting applications. So we're going to try a few different types of problems as well. That doesn't seem like it would be a mean value theorem problem, but it really is. So suppose that 3 is less than or equal to our derivative is less than or equal to 5 for all values of x. So I know my derivative is bounded between 3 and 5. We want to show that if I look at f of 8 minus f of 2, it's got to be trapped between 18 and 30. Okay? So this is kind of a hidden mean value theorem in disguise. And the reason I can kind of gauge that it's going to be mean value theorem is because I'm looking to bound the difference in two y values. So I want to apply mean value theorem on the interval starting at 2 and ending at 8. So I still need to show all of my hypotheses are satisfied. I need this function to be continuous. I need this function to be differentiable. But because I know the derivative exists for all values of x, I'm immediately going to get that. So since f prime of x exists for all x, f is a differentiable function. Because it's differentiable, it's continuous everywhere. So remember, differentiability guarantees us continuity. So in particular, I want to look at f of 8 minus f of 2. That's exactly what goes in the numerator on my mean value theorem. So in particular, we can apply mean value theorem on the interval from 2 to 8. And so that tells us there exists a c in the interval 2 to 8 such that if I look at the difference in f of 8 and f of 2 over 8 minus 2, it will equal the derivative for some value c between 2 and 8. Well, f of 8 minus f of 2 is just 6. And really, if I then go ahead and multiply both sides by 6, this tells me my difference in f of 8 and f of 2 is going to equal 6 times my derivative. Okay? But I know what this derivative is trapped between. It's always between 3 and 5. So using that to my advantage, since the derivative evaluated at c, doesn't matter if it's x or if it's c in here, is trapped between 3 and 5 for any value of c, we have 6 times the derivative would be less than or equal to 6 times 3 or 6 times 5. So 6 times my derivative is always trapped between 30 and 18. But 6 times my derivative is exactly the difference in these two y values. So what we get from here is that 18 is less than or equal to the difference of f of 8 and f of 2, and that is bounded above by 30, which is exactly what we wanted to show. Okay. All right. Now we have one more useful alternate for this form. So we know f of b minus f of a is the derivative times b minus a. If you just go ahead and add this over, you get another form for that mean value theorem. Okay. So let's apply this useful alternate to answer a particular question. We want to find a function f that has derivative 8 and it passes through the point 0, 5. So again, I know the derivative. We're told it's existing for all x. Immediately, I'm guaranteed continuity and differentiability. So applying all that, f prime of x exists for all x. So f is a differentiable function. Thus, it's continuous everywhere. So differentiability implies continuity. Now, the thing you want to note is we're told it passes through the point 0, 5. So this is 0. 5 is my function evaluated at 0. Okay. I'm going to pick another point on my function. If I choose an arbitrary x, the y value corresponding to it is f of x. Okay. So I'm going to go ahead and apply mean value theorem to the interval from 0 to x to help me find this function. So applying mean value theorem to the interval 0 to x gives us, using the second form, f of x equals f of 0 plus f prime of c times x minus 0. Well, f of 0 is 5. My derivative is always equal to 8. And x minus 0 is just x. So immediately now, my function that passes through the point 0, 5 and has derivative 8 is 8x plus 5. So mean value theorem is actually able to help me create a function that had specific properties. And you can check that it does satisfy that. If I take the derivative, it is indeed always 8. And if I plug in 0, that would be 5 plus 8 times 0. So it passes through the point 0, 5. So this line satisfies those two properties. So mean value theorem is a very useful theorem. It appears in a lot of proofs for things. So a lot of these techniques we're going to go through rely on the hypotheses and conclusions of mean value theorem. So it's a pretty neat thing. And geometrically, it has those interpretations. So we're going to keep heading with this in the next section. We're going to be learning about properties of different functions.